This lecture is about heuristics and local search. First, let's recall what an optimization problem is. Well, in an optimization problem, we have input instances. For each input instance, we have a set of feasible solutions. And for each feasible solution, we have a value. And what we want to do is we want to find a feasible solution that maximizes or minimizes the value of this solution. For example, in the graph coloring problem, which is a minimization problem, our input is a graph. The feasible solutions are all the proper colorings of the graph. So all the colorings where no two adjacent vertices receive the same color. And the value of a coloring is just the number of colors that we used. So what's a heuristic? A heuristic returns, so it's an algorithm that returns a feasible solution. Typically, there's no guarantee on the value of the solution that the heuristic returns. And ideally, heuristics are fast, easy to implement, and return satisfactory solutions for many instances. So to evaluate a heuristic, we could implement it and run it on a set of benchmark instances that we care about, and then we can compare heuristics like this. What is local search? So in local search, for an optimization problem, we are given a feasible solution, and now a local search algorithm will explore the local neighborhood of that solution, which means that it will check whether there's an improved feasible solution that can be obtained from the given feasible solution by a small modification. So for example, we could ask, is it possible to recolor some of the vertices, so just a small number of vertices, such that we end up using fewer colors? Or in the traveling salesman problem, so the feasible solutions are tours that visit all the cities. And now we could ask, if we're given such a tour, is there a shorter tour that can be obtained by the first tour by just swapping some of the cities? So and these modification operations, they define the neighborhood in our space of feasible solutions. And so you could use multiple kinds of modification operations, and this would give you a different space. We'll do two case studies. One is on graph coloring, and the other one is on treewinds. So we'll start by graph coloring, and there are no slides for this. So we'll just discuss heuristics for graph coloring and a paper by Hartung and Niedermeyer. So if we want to think about heuristics for graph coloring, so let's see. So in a graph coloring problem, we're given a graph, and we want to partition the vertex set into few independent sets. And of course, since we want to use few independent sets, we kind of want to maximize the size of those independent sets. So one kind of heuristic could be that so we delete a large independent set of our graph. We want to delete some large independent set. So we start with having used 0 colors, and then whenever we delete the large independent set, well, we increase the number of colors that we used, and then, well, we keep repeating this. So the second point here, we keep repeating it until our graph becomes empty. So we won't care so much about the details, but this is the main step. We delete the large independent set, and k increases by 1. So now how do we find the large independent set? Of course, independent set is an NP-hard problem again, so we might need to also use a heuristic for finding a large independent set. And one of the simplest ones is just a greedy algorithm. Let's call it greedy IS. of a graph G. What does it do? So it selects a vertex, and now basically it adds this vertex into our independent set, and then it tries to find an independent set of, well, the graph obtained by removing this vertex and all its neighbors. And so we have to discuss how to select this vertex. So what the algorithm will do, it will return, well, a set containing V and whatever it gets from a recursive call by calling greedy_is of G minus the closed neighborhood of V. And of course, well, we want this graph to still have many vertices left because we want to maximize the size of this independent set. So we'll go ahead and select a vertex with minimum degree. So this is one possible heuristic. Of course, you could try and define a randomized algorithm where you prioritize vertices with small degree to be selected. Okay, so this is one kind of heuristic for graph coloring. Another one would be as follows. So we order our vertices in some way. So we have n vertices. So, and now we will color the vertices starting from V1 and then going to V2 and then V3. So let's say some vertices have already been colored. And when we color the next vertex, so let's say we color Vi, so vertex Vi, by giving it the smallest color that is still available. So we'll start from color 1. So V1 will get color 1. And then V2 will also get color 1 unless it's adjacent to V1, in which case it would get color 2. Now V3 gets the smallest color that's still available if we consider that V1 and V2 have already some colors. So we color Vi with the smallest color. So let's say that doesn't conflict with any previous coloring. Let's just say this is the smallest available color. Okay, so which ordering should we choose? So would we first color the small degree vertices, or would we prefer to start with large degree vertices? Or should this all be done in a connected way? It's not very clear. But so what is clear is that when we have a large degree vertex and we have already colored many of its neighbors, then we have quite a lot of constraints on the color of this vertex. So coloring large degree vertices seems more difficult than coloring small degree vertices. Because if we have a vertex of small degree and many of its neighbors have already been colored, then, well, still that doesn't imply as many constraints as if we have the same situation for large degree vertices. So in this ordering here, we would prefer to order large degree vertices first. Because at the moment where we color large degree vertices, we don't want there to be many constraints already. Okay. So we order the vertices from large degree to small degree, and then we process the vertices in this order, and then each time we color a vertex, we give it the smallest available color. Okay, so this is a well-known heuristic for graph coloring. So let's say that we want to find a coloring with at most k colors. And so let's say that when processing vertices, v1, v2, etc., so we give them some colors, and then suddenly everything is still fine. We still don't exceed k colors up till vertex p minus 1. And then when we consider vertex p, we discover that, well, it is adjacent to a bunch of vertices, and all the colors from 1 to k have already been used up by its neighbors. So now we need color k plus 1 for this vertex. So we are not happy, because we wanted the coloring with at most k colors. So what we could do now is, well, we have this graph now on p vertices, where we have used k plus 1 colors. And the k plus 1th color is only used for the last vertex. So everything up to here is colored with k colors. And this new vertex here needs color k plus 1. So now we could check, well, is it possible to modify the coloring that we have already via a local search algorithm, such that actually we can color everything with k colors. So everything up to and including vertex VP. So this is what Hartung and Niedermeyer concentrated on. So the problem they considered is called incremental conservative k, no, not coloring, but list coloring. So list coloring is similar to just coloring. So in coloring, every vertex can be colored with colors from 1 to k. And in list coloring, we have a list of colors from 1 to k, or a subset of colors from 1 to k, that's available for each vertex. So the input of their problem is a graph G. And now a vertex X that we have trouble coloring. We have a list of colors for each vertex. The list LV, which is a subset of colors from 1 to k for each vertex. We also have, well, a list coloring F for the graph G minus V, minus X. And we have like a parameter that tells us how much we are allowed to change F. So this is C, which is a natural number. So C stands for change. Okay, now the question is whether there exists a new list coloring F prime for all of G that is the same as F except on at most C vertices. So such that, well, the number of vertices that get recolored, so the cardinality of the set of vertices where we exclude X, such that F of this vertex is different from F prime of this vertex. The cardinality of the set is at most C. And And this is a question. Okay, so now I have some results about this problem, and some of them are parameterized results. The first result is that, well, this problem is NP complete. NP hard, I guess, or NP complete. It's a decision problem, so we can say it's NP complete. And so they have this even when G is bipartite. So of course, when G is bipartite, the coloring problem is not NP complete, because we can color bipartite graphs with two colors easily in polynomial time. But when some of the vertices are already pre-colored and we are only allowed to change a few of these colors, it turns out that the problem becomes NP complete. So that's bad news. Another result they have is that the problem is W1 hard. And whenever I say W1 hard or FPT, I have to tell you what the parameter is. So, and this W1 hardness result was for parameter C. So parameterized by C, this problem is W1 hard. But spoiler alert, they considered other parameters, and in particular combinations of parameters. They have also an ETH result, so under the exponential time hypothesis, they showed that, well, the problem, so this problem IC K LC has no algorithm with running time n to the little o of c. Okay, so not only is the problem W1 hard for parameter c, but even if we allow an exponential function in n and c, it cannot, so this exponential function cannot be n to the little o of c. Okay, and so the next result they had is an FPT result for parameter k and c combined. So they gave an algorithm with running time k times k minus 1 to the power c time algorithm for the problem times the polynomial. Meaning that, well, the problem is FPT for parameter k plus c. Let's zoom in onto this result and see how it works. So we want to, okay, first of all, we want to give a color to x. X doesn't have a color yet, so we have to assign it some color. And we can branch into all k ways of assigning a color to x. So we need to color x, and there's k ways of doing this. So we can consider all of them. Okay, so now let's assume we have colored x with some color I. Now, of course, there could be a conflict. So if for some coloring of x there's no conflict, then we're done. Assume there's a conflict for each color of x. So now we have to continue. So now we actually have to recolor some of the vertices. So, okay, so our color for x is now fixed. We are not going to recolor x, and we are only going to recolor other vertices. Okay, so and once we recolor a vertex, we are never going to recolor it again. So once we recolor a vertex, we freeze the color, and We are not going to modify it again. Okay, so now we need to resolve all the conflicts. And of course, when we recolor a vertex, we might create new conflicts. And the conflict is, of course, two adjacent vertices that have the same color. And every time we resolve a conflict, well, to resolve a conflict, we are going to try and, well, recolor the vertex whose color is not frozen and give it a new color. And so we select this, we select one vertex that has a conflict, and now we are going to try to recolor it, and of course there's k-1 ways to recolor a vertex. So to color x we had k possibilities, and to recolor a previously colored vertex we have k-1 possibilities. And we are going to branch in all of these ways, and of course this might create new conflicts, so we just keep a list of all conflict vertices that we need to recolor. And at some point, we either find that we find a valid coloring where we have recolored at most C vertices, or we find that, well, recoloring only C vertices is not sufficient to give a coloring with K colors. Okay, so the depth of our search tree here is something like C plus 1 or 2. And how many leaves do we have? Well, this is a branching into K possibilities, and then for all of the other C branchings, we have k-1 possibilities. So we have a search tree whose number of leaves is k times k-1 to the power c, which is exactly this running time here. Okay, so this explains how this branching algorithm worked. Another thing Hartung and Niedermeyer did was they designed a kernel with 3 times k-1 to the power c vertices. So this is an exponential kernel if we consider the parameter k and c. And this is actually quite readable. If you download the paper, then you can read how they obtained this kernel. Another result they had is that there's no polynomial kernel, unless some complexity classes collapse, so unless NP is actually a subset of co-NP/poly. So you don't need to know what this means, just know that it's unlikely. So, and we don't expect that so this size of this function here can be reduced to a polynomial. They also looked at trewitz as a parameter, and so they gave an algorithm with running time O star of k to the power w plus 1, where w is the width of a tree decomposition that we also get in the input. So let's say if a tree decomposition of width w is available. And by now you should be able to understand what all of this means. Another result they had is a polynomial kernel for, well, we said there's no polynomial kernel, but they have a polynomial kernel when the input graph is not a general graph, but a unit interval graph. What's a unit interval graph? Well, it's a graph that can be obtained as follows. So we have a set of intervals. All of them have the same length. Let's say this is just one axis, so an axis of real numbers. So we have a set of intervals, and we draw them on the axis, but well, since we couldn't see them very nicely, if I draw all of them on the axis, I draw them slightly above. And now the associated graph is, well, a graph where we have exactly one vertex for each of these intervals. Let me try and draw them on top. And when two of these intervals intersect, then we have an edge between the vertices in this graph. So these are adjacent and these are adjacent. So this would be just a path, assuming that we don't have any overlap between those two intervals. Okay, so our graph is an interval graph if it's possible to assign an interval of length 1 to each of the vertices, such that the edge relation of the graph is defined by the intersections of the intervals. So in other words, interval graphs are intersection graphs of unit length intervals. Okay, so the main point about this paper was to look at this heuristic for graph coloring and try and turbocharge it. So we're looking at this heuristic, and sometimes it gives us a number of colors that's a bit too large for our liking. And now we want to do some local search we want to do some local search in order to improve the number of colors we used. So whenever we have to use color k+1 according to the heuristic, we could try and, well, change some of the colors so that we can actually color everything up to now with just k colors. And of course, we can't do anything to k because, well, the number of colors we use might just depend on the graph that we are given. But we can adjust c. So if our algorithm is too slow for some value of c, we can always try with a smaller value of c and check whether this actually gives us a better coloring or not. And if not, then maybe we're just unlucky. Okay. The other case study we consider is trivids. So this is based on a paper by Gaspers, Gudmundsen, Jones, Mestre, and Rimele. Okay, so I need to give you a little bit more background on tree decompositions in general. So the problem we want to solve is, well, the input is a graph. The feasible solutions are tree decompositions, and the value that we want to minimize is the width of the tree decomposition that we find. Okay, so of course we know what tree decompositions are. So we just have bags that consist of vertex sets of our graph. And, well, these bags, they are arranged in a tree-like fashion. Okay. The first thing I want to do is to think about what happens, or which other graphs have the same tree decomposition. Or what is the densest possible graph, dense in terms of the ratio of number of edges to number of vertices, that has the same tree decomposition. Well, so if we have this tree decomposition, so this is a tree decomposition not just for one graph, but for multiple graphs. And what we can do in order to add a maximum number of edges into our graph, so that this tree decomposition is still a valid tree decomposition, is to actually take each bag and we make it into a clique. So we add edges to our graph such that, well, this bag becomes a clique. So now what we can do is we can make each bag into a clique. So this means that whenever there are two vertices inside a bag that are not adjacent to each other in the graph, then, well, we add an edge between them. So what do we get by doing this? So by doing this, we actually obtain a chordal graph. So what's a chordal graph? So a graph is chordal if we don't have any cycles of length at least 4 that have, well, no additional edge. So a chord of this cycle would be an edge like this or an edge like that. If we don't have a chord, then we have a chordless cycle. So chordless cycles are forbidden, so we can't have those. So whenever we have a cycle of length at least 4, our chordal graph must have a chord that connects two non-consecutive vertices of this cycle. And of course, so let's look at this graph. So a cycle of length 4. So let's say this is vertex 1, this is 2, 3, and 4. So one possible tree decomposition would be, well, with 1, 2, and 4 in one bag. We know that the tree decomposition must have widths at least 2, because, well, there's a cycle in this graph. And the other bag could be 2, 3, and 4. This is a valid tree decomposition. So now, if we make, well, each of these bags into a clique, what do we get? Well, with 1, 2, 3, 4, we still have the same edges as before, but now we made sure that 1, 2, 4 is a clique. So this edge appears, and also that 2, 3, 4 is a clique. That's the same edge. Okay. So if we make these into a clique, then we get this chordal graph here. Okay, chordal graphs are very well studied, and it is known that chordal graphs have clique trees. What is a clique tree? Well, it's basically the same as this tree decomposition here, where we just merge some of the bags. Because, well, in a clique tree, we want each bag to actually represent a maximal clique in this chordal graph. Okay, so our problem now becomes, well, we actually want to find a chordal graph where we want to minimize the size of the largest clique. Because, well, we know that if we have a clique in a graph, all the vertices of this clique must occur in some bag, and actually the tree decomposition of a chordal graph is a clique tree, or kind of a clique tree. So we know that, well, what we want to do is, well, we want to add edges to our input graph so that the graph becomes chordal, and we want to minimize the size of the largest clique of this chordal graph. Okay, so this is an aside. So let's focus on the tree decompositions. So tree decompositions where every bag becomes a clique. So remember that we want to find a heuristic for finding a tree decomposition that doesn't have large widths. Okay, let's discuss a bit more about these kinds of tree decompositions where the bags are cliques. So, okay, so we can take some tree decomposition of the graph, and we'll make it into a nice tree decomposition. Okay, so now what I want to do is I want to start from the leaves of this tree decomposition. And actually what I want to do is I want to start from the first forget node. Let's say we do the following. Let's say we define the following operation. So if there exists leaf T in the tree decomposition with parent T prime, and so the bag of T is included in the bag of T prime, meaning that, well, T prime is an introduced node. Then we remove T. We end up with still a valid tree decomposition of our graph, because, well, since this bag of T is included in the bag of T prime, we still cover all the edges that we covered before. Okay, so by doing this repeatedly until we can't do it anymore, until every leaf will violate this condition, we now have, well, if now we look at a leaf T with parent T prime, then, well, we know that T prime is a forget node. So T contains some vertex, let's call it X, that is not included in the bag of T prime. So the bag of T is equal to the bag of T prime union this vertex X. So now what we want to do is we want to get rid of X. So we want to say, okay, our tree decomposition can be obtained by a tree decomposition for everything except X by adding this new bag here. Okay, so what we want to do is we want to remove X. Well, from both G and from the tree decomposition. And so what we want to do is, well, we want to guarantee that later on we can insert X again. So once we find the tree decomposition of the remaining graph, we want to be able to add, well, this new bag here. This new bag that's adjacent to this bag. So we want to guarantee that such a bag exists. And to do this, well, what we are going to do is we will make the neighborhood of X into a clique. Okay, so now if the neighborhood of X is a clique, we are guaranteed that some bags contains all the neighborhood of X. So the neighborhood of X is in here. And so now we can add this vertex, so this node here, into our tree decomposition. Okay, so and we will repeatedly do this. So we select a vertex and we make its neighborhood into a clique, and then we remove the vertex. And by doing this, this will define a new bag of our tree decomposition, namely this bag here. What does it contain? It contains X and all its neighbors. So this defines a bag of size so the degree of X plus 1. Okay, so we're going to try and find a perfect elimination ordering. So just as an aside, if we have a caudal graph, well, let me tell you what a perfect elimination ordering of a caudal graph is. So perfect elimination ordering of a caudal graph is an ordering of the vertices, of all the vertices, such that, well, the neighborhood of the first vertex is a clique. So we have a PEO, perfect elimination ordering, is an ordering of the vertices such that the neighborhood of V1 is a clique, and, well, this is true recursively. So V2, V3 up to Vn is a perfect elimination ordering. So whenever we take, so the perfect elimination ordering will guarantee that we can process the vertices in this order. Every time we look at a vertex, we know that the neighborhood is a clique, and then we remove this vertex. Now if we look at the next vertex, its neighborhood is a clique, and then we can remove that vertex. So basically, if our input is a caudal graph, then, well, we are guaranteed that, well, such a tree decomposition exists, where we never need to add any edges to make the neighborhood of X into a clique. And we also know that what we are looking for is actually a supergraph of the input graph that is caudal. And so for every graph, it is possible to come up with a perfect elimination or with an ordering such that if we make the neighborhood of each vertex that we process into a clique, then, well, we can find a minimum width tree decomposition. But of course, finding this ordering is non-trivial. So typically this takes exponential time, but we can define a heuristic that is based on this ordering. So our heuristic is, well, we choose some vertex, we remove the vertex from the graph, and we make the neighborhood into a clique. Okay, so and in the end, the width that we get in the end is the width of the tree decomposition that is defined according to this ordering of choices is the maximum degree of V that we encountered. So I don't have the plus 1 here because, well, the width is the maximum bag size minus 1. Okay, and then I keep doing this. So I keep choosing a vertex, I remove it, I make it into a clique, and so in the end, the width is the maximum degree that I encountered in that way. So this tells me somehow of how I should choose this vertex. So I could choose, so an obvious choice is of minimum degree. So the downside might be that, well, if I choose a vertex with minimum degree, and actually my neighborhood, the neighborhood of this vertex is an independent set, then I would add many edges, which might have adverse consequences later on. Instead, maybe it would be more beneficial to consider a vertex that has already many edges in its neighborhood. So alternatively, instead of a vertex of minimum degree, we could select one with minimum, let's call this fill-in. So the fill-in is the number of edges that we need to add to our graph in order to make the neighborhood of this vertex into a clique. So this now defines two heuristics. But each time we just want to find some ordering of the vertices. This ordering will define a tree decomposition, and we want to minimize the width of the tree decomposition that we find. Okay. So now we can play the same game as before. So let's say we have already processed some vertices. We want to find a tree decomposition of width at most k. But now the next vertex that we add into our ordering will define a bag of size more than k plus 1. Let's say that we want to find a tree decomposition of width at most k. So, and our heuristic now has computed an ordering of a few vertices. So it was able to find a vertex with degree at most k. Now it eliminated it, creating a bag of size at most k plus 1. Then it found another vertex and another one, etc. Until at some point, so after p steps, let's say after p minus 1 steps. So vertex p minus 1 was still okay, but now it wasn't able to find another vertex of degree at most k. So, and of course we can eliminate only vertices of degree at most k, because this will define a new bag of size k plus 1. So bags of size k plus 1 are the maximum size bags that are allowed in a tree decomposition of width at most k. Okay, so after p minus 1 vertices, we cannot find another vertex v sub p that has degree at most k. So we are stuck. So here we are stuck. So now we want to go back a little bit. So we want to basically undo so some number of steps. Okay. So up to some vertex v sub p minus l. So L is the length of this elimination ordering that we undo. Okay, so now we still keep this partial elimination order. And now our question will be, well, can we go up to, well, can we add L vertices now, or L plus 1 vertices? Can we add L plus 1 vertices and not get stuck at the same point where we got stuck before. So can we go at least one vertex farther than before? So that's the problem we are considering. So let's call it partial elimination order. Because, well, we don't necessarily want to go until the end of the graph, but we want to go a little bit further. So we want to do a little bit better than the heuristic was able to do. So our input is a graph G. We have, well, a length, let's call it L instead of L plus 1. So we have a number of vertices that we want to add into our partial elimination ordering, let's call it L. And we have an upper bound on, well, the width of our tree decomposition. So we have an upper bound on the degree of the vertices that we eliminate. So now the question is, does there exist like such a partial elimination order of G of length L? And so every time we eliminate a vertex, we create a bag of size at most k, leading to width at most k. So let's say the width of this partial elimination order is the maximum degree of a vertex that we eliminate. So we say that the width of this partial elimination order is at most k. So that's the max degree of an eliminated vertex at the point in time where it gets eliminated. Okay. And in this paper that's called turbocharging tree-width heuristics, this is the problem that got considered. And so the main theorem is that, this problem is fixed parameter tractable, parameterized by L plus K. Okay, let's look at the proof, how this works. So one thing to notice is that, well, we can eliminate vertices with degree at most k. So those are kind of special for us. So let's define S as the set of vertices such that, well, the degree of this vertex is at most k. So we take all of the vertices of degree at most k and put it in this set S. Okay, so of course we might be in trouble when we eliminate a vertex from S, because now, well, there's new edges that appear because we make the neighborhood of this vertex into a clique. So new edges appear, and, well, this might mess up the other vertices of S. So the other vertices now might have degree larger than k. So we want to avoid that we want to eliminate vertices. I want to select a large number of vertices and eliminate them in such a way that, well, we don't mess up the other vertices that we select. So let's say we have this set S here. So we could have many vertices in here. All of them have degree at most k in the graph G. And okay, now when we eliminate this vertex here, and, well, all its neighbors are outside of S, then we're pretty safe because, well, we don't mess with any other vertices from S. But now, of course, we could want to eliminate some other vertex that has some neighbors in S. And now, well, their degree gets increased. So kind of what we want to do is make sure that, well, if we can, we might want to select an independent set in S. And we are sure that we can eliminate all of those vertices because, well, all of them have degree at most k. And whenever we eliminate one of them, we don't affect the degree of the other vertices of this independent set. So what we can do now is we define this vertex at I, which is, well, of course, independent set is again an NP-hard problem, so we're going to use our greedy algorithm that we defined earlier, greedy IS, and we execute it on the graph induced on S. So I will now be an independent set inside S. Okay, and now we do a case distinction. So the first case is where this independent set is large enough that we can just process every vertex in I and finish the job. Let's say the size of I is at least L. Okay, so what do we have? So we know that eliminating a vertex V in I does not increase the degree of any other vertex in I. Okay, so this means that we can eliminate all of I. Okay, and well, that's all we need because, well, I has size at least L, and we only need a partial elimination order of length L. So in this case, we are done. So the other case is where I has size at most L minus 1. Okay. So if I has size at most L minus 1, what do we know? So we know that S cannot be too large with respect to L and K. So let's see. So when our greedy algorithm added a vertex into I, it deleted, so every vertex in S has degree at most k. So it deleted at most k plus 1 vertices from the graph. So every time it added a vertex into I, it deleted at most k plus 1 vertices before it continued. So the size of S is at most L minus 1 times k plus 1. Because every time we add a vertex, we're basically going to say that there's k plus 1 vertices that we're not going to add into the independent set anymore. Okay, so now S is not too large. So, well, this is an FPT function for the parameter L plus K, right? Okay, we also know that the vertices in S are the only vertices that are possible as a first choice for our partial elimination order. So when we add our first vertex into the partial elimination order, this must be a vertex from S because, well, any other vertex has too large of a degree. Okay, so we know that the first vertex of our partial elimination order is in S. So what we are going to do is we branch into L minus 1 times K plus 1, and at most as many subproblems. Now, how is each subproblem defined? Well, we have a subproblem for each vertex in S, which is our choice as the first vertex, where we recursively execute the algorithm. We run our algorithm recursively, but on the graph where we have eliminated the vertex V. How do you write this? So V disappears and its neighborhood becomes a clique. So let's say we write this elim G, V, which is the operation that makes the neighborhood of V into a clique and deletes V. Now, we still want to find a partial elimination order of the remaining graph of length L minus 1 and width at most K. So the width doesn't change, of course. Okay, so what have we done now? We have branched into, well, this many subproblems. And each time L decreases. So we make some progress in terms of L. So the height of our search tree will be at most L, and the width, well, the number of leaves will therefore be at most L minus 1 times K plus 1, all of it to the power L. So our final running time will be something like this. Of course, every time we branch into a subproblem, we can again check whether our greedy algorithm finds an independent set that's large enough. If not, then we again consider every vertex in S to branch on. Okay, and so what we have seen now is, well, a greedy process that constructs an elimination ordering. And, well, this elimination ordering gives us a tree decomposition. And ideally, we want a tree decomposition with small widths, and we saw that, well, whenever we eliminate a vertex, the degree of this vertex determines the width that we get for this bag. And of course, sometimes we are not happy. We might add bags that are too large, but in this case, we can sometimes do some kind of a local search. And again, here we can adjust L. So whenever we have to do a local search, we can decide how far back we want to go. And of course, sometimes we need to go very far back, and in this case, well, this approach is not very viable, but at least we can try whether we can slightly improve the heuristic by our parameterized subroutine here. Of course, there's a few more results in this paper, and the other variant of the heuristic where we choose a minimum fill-in vertex here has also been considered and turbocharged. These are the references of this lecture, and that's it for today.